Aloha, biostatisticians. Here's the video to walk you through step by step the lab for doing simple linear regression with transformations. I'm in my office here. Eddie's hanging out, so all good. Let's start by going to La Lima. In La Lima, you'll see the assignment Lab 9 Transformation Seeds, SLR. This is what it should look like for you. Scroll down to the instructions, assignment instructions. I've tried to make these very clear so you can follow through step by step easily. Step 1 is to open the attached regression seeds notebook.rmd file, which will open in a separate tab in your browser. Then select and copy all the text. So if you go down to where you see regression seeds notebook, this link down here under additional resources for assignment, click here and you'll see it opens up in a new tab, and it's a bunch of text, and that's not what you want. You want an R notebook. It's all in there. Don't worry about it. Here's what you got to do. Select everything. I use Control A to select everything and then copy everything. I use Control C. If you're on a Mac, I think it's Command, does the same thing. Then you go over to R, open up your R Studio. Open up your R Studio and go to File, New File. Go over to New File. There's a lot of options. Select R Notebook. R Notebook. Select R Notebook. Let's maximize that so you can see everything. And you'll see you get this default R Notebook that has some information about how to work with notebooks. Handy, right? This is handy. But we're not going to use it right now. We're actually going to select all of this and we're going to delete everything from here. And what we're going to do instead is paste in our code from La Lima. Control V, paste everything in there. Great. Here's our code from La Lima. It should work. Now what we have to do is save this file. Go back up to the File menu. Select Save As, ... And now you can choose where you want to save it and the name of the file. I strongly recommend that you create a new folder in a place that you can easily find it again, so you can use this as a reference for later. So I'm going to, for now, put this on my desktop, but you can choose anywhere you want that makes sense to you, or you could put it into a folder that you have all your biostats codes saved into, right? So here I'll go to my desktop and I will create a new folder. So create new folder. And I'm going to call this new folder Lab 9 SLR Transformations Seeds, because the seeds are the topic. And now I'm going to be able to easily remember that this is where I have information about simple linear regression and transformations. Oh, and that was the seeds example. That's right. That was the one we used. If you name it with something that helps you jog your memory, then weeks from now, when you're getting ready to study for the final, you'll be able to go like, oh yeah, what was that again? What is that? Okay, so open up that folder, and now where you have to save it as something. So you go down to File Name and name it something. I can actually name it the same thing. Lab 9 SLR Transformations Seeds, right? And it will save it as type automatically .rmd. Save that. Now we're going to go back over to La Lima, and go back to the assignment tab, right? So we did step 1. We opened the notebook in a new tab. We selected and copied all the text. We opened our studio. We went to File, New File, our notebook. We selected and deleted all the text in the new R notebook. Then we pasted all the text we copied from the regression seeds notebook RMD into the new R notebook. And then we saved our notebook in an appropriate place with an appropriate name. Remember, we just did all that. We're like halfway through. Now the next step, step 6, is download the attached Seeds CSV data file. So we go down here under additional resources for assignment, and you see where it says seeds.csv. Click that and it will automatically download. It will probably save it into your downloads folder. That's what it does for me. So if I go up here, I see this little symbol says downloads. Oh, okay. Oh, there it is. And I don't want to open it. I want to save it somewhere else. So I see this little folder icon. It says show in folder. I click there. Okay, great. Here are all my downloads. And I can take this. I'm actually just going to cut it out of here. I'm going to go over to the desktop and I'm going to put it into that Lab 9 SLR Transformations Seeds. Now what I have here is I have my RMD notebook that I just made and saved, and the seed CSV file. They're in the same folder. And you'll see this other file just popped up out of nowhere. Like, what's this third file? Well, this is a HTML document that's automatically created when you create our notebook and you say that the default output should be HTML. Great, we want that. It's good. Okay, so we've got all that. Okay, we got that all in our, okay, we got it all in one place, right? We've got it all in one folder. We've got it all saved. Now we can get going on our assignment, right? Isn't that the next step to do? Let's see, it says download the attached CSV data file, save the seeds.csv data file in the same folder as your R notebook.rmd file. Check, check, did that. Then complete the attached R notebook by running the code and answering the questions at the little arrow prompts. Then knit the complete notebook to HTML, Word, or PDF and submit to Laulima as an attachment by the due date, which is Monday. So you got a little bit of time. I'll try to get this out for you in the next couple hours. Great. Now let's go to R and I will walk you through what we got to do to get this done. Get this done, right? Step by step. Okay. SLR transformation in R. So we have talked about doing linear regression quite a bit. And I have alluded to or foreshadowed that we will eventually talk about transformations. So we're going to do that today. And this is partially to kind of get you back into the swing of doing stats after our break. Just remember, oh yeah, here's what we do in stats. It's kind of an easy one, but it's going to teach you something really important. And that really important thing is doing transformations, which is commonly done in real stats all the time. You're going to need to know it. I'll just introduce it to you here. It'll be like magic and awesome. You'll love it. It's fun. And we're going to use a data set about seeds. And we're going to come back to this idea of biology. We've talked about a few different things. We've talked about some different things, but we're going to really stick with biology here. So according to the principle of allocation, you remember that from ecology? Yeah. Species can only give so much energy to each aspect of life history. Is that ringing a bell? Yeah, okay, good. If this is true, that's the hypothesis, right? Then trees that produce many seeds will have small seeds, and trees with fewer seeds will have larger seeds. Okay, so the number of seeds will predict the seed size. To test this hypothesis, and now remember, a statistical hypothesis is different than a scientific hypothesis. It's not just like null. It's like more of like a theory that you want to like examine the assumptions, right? And test. Our research team collected seeds from tree species across North America, or some research team did. I got this data from another professor. They counted the number of seeds produced by the tree and measured the weight of the seeds. We want to know if our data support the principle of allocation. If our data support the principle of allocation, then the number of seeds or seed count in our data will predict the size of seeds. In this case, we measured seed weight as the size. I just want to bring this up that if you're measuring the size of something, it can be a little tricky to measure like the length or the diameter of something like a seed because it's not regular or something kind of three-dimensional and round. It's hard to like put a ruler there and measure it. You can use calipers maybe, but which side? And it's easier to just measure the weight. But then you have to think about, well, what about water weight makes up a lot of the weight of something. Is everything desiccated to the same humidity? Assuming that they did that, assuming this was a great research team and they thought about that, they're like, well, water is most of the weight, so we probably should have had to desiccate all the seeds to the same humidity level and then weighed them so we could have a good comparison. 100% they did, right? We're just going to make that assumption that they did a good job. That's what we would have done, right? Absolutely. All right, and then we come down here to question 1. And these questions are really just for me to make sure that you are paying attention. Pay attention, wake up, write something down. So question 1, what is the predicted direction of the relationship between seed count and seed weight? Okay, so think about that. What did we just say? We just said, if our data support the principle of allocation, right? This is our prediction. Then the number of seeds or seed count will predict the size of seeds. Wait, so what are we trying to predict here? We're trying to predict the seed size. We're trying to predict weight. And the number of seeds is the predictor, right? And what do we think is going to happen, right? We think that trees that produce many seeds will have small seeds, right? And trees with fewer seeds will have larger seeds, so that seed size and seed count will be inversely related. As you get more seeds, you get fewer seeds, right? So this would be a negative relationship, You should see the line going down on the graph. So what is the predicted direction of the relationship between seed count and seed weight? Oh, this is pretty easy. We'll just say the predicted direction of the relationship between seed count and seed weight is negative. And no, it's not okay to just write negative. That's not a complete sentence. You are college students. You can do better than that. Process. All right, the process that we're going to use is the same as we've been doing every time. And you notice I repeat this same process over and over and over because I feel like the more times we repeat it, it'll start to just become ingrained in your psyche that this is how we do it, step by step. We ask the question, and then what we do is we say, write out the statistical hypotheses, right? Write out the statistical hypotheses, check our assumptions, right? Every test has assumptions. We got to check them, run our analysis. And I know this is an iterative process. We actually have to run the analysis and then complete the checking of assumptions, because you have to run the analysis to get the data of the residuals to see if the assumptions are met for the residuals. But so this is kind of like a cyclical, iterative process. And then you interpret and display the results. Once you have met the assumptions, you're like, okay, we're good with that. Now, what do these results mean? And how do we show them? How do we graph them? We want to communicate them to other people, right? This is cool. We found out something neat. We'll show the world. And then write the conclusions in a compelling way using your results as supporting evidence. Right? Great. That's the process, step by step. And that's what we do every time. I hope. If I ever forget something, let me know. All right. Okay, question 2. Write the null and alternative hypothesis for the simple linear regression, SLR, right? So the null hypothesis, remember, we're talking here about relationships. Relationships, it's so hard. So the null hypothesis is that there is no relationship, or that the slope of the regression would be 0, right? 0, null, nothing, right? The HO is that there is no relationship between seed count and seed size or weight, right? In other words, the slope of the regression will be equal to 0. And the alternative hypothesis, that's easy, just the opposite. There is a relationship between seed count and seed size. The slope of the regression is not equal to 0. I use this this symbol here, the two arrows going opposite directions, to mean not equal to. That's another symbol for not equal to, because it's not easy in our notebook to bring up the not equal symbol. Or we can just type it out, not equal to 0. Fine. Again, you got to write it all out. Once you write it all out, great. Now we can go to the next step, which is loading the data. And this is where a lot of people get stuck. Just be sure that the seeds.csv file and this R notebook are saved in the same folder. If you haven't saved the notebook, that won't work. If you have that seeds CSV in another notebook, that won't work. If you do have it saved, if you have them both saved in the same folder and it still doesn't work, just try restarting R. Okay, just try restarting it. Okay, great. And you might need to install this library read R. If so, there should have been a little yellow banner right at the top that says to install it. Just click that, it installs really fast. But maybe you already have it installed. And then you can run this code, which basically what it does, it says to R, read the CSV file. What CSV file? Oh, this CSV file. It's called seeds.csv. Notice we don't specify a path name because it's expecting this file to be in the same working directory, the same WD working directory as the notebook. And it should have automatically set the working directory as the location where the notebook is located. Sometimes it can get goofy like that, but that's what it should be doing. It should say, okay, it's like it's self-aware or something. You know, it's like the notebook's like, oh, I'm here in this notebook. Oh, and look, there's a little CSV file here with me. Oh, I can load this in. You know, that's the first place it looks. And then this show column types false. I don't really remember why this is, that just, it works. Run this chunk by hitting the play button. And if all goes well, then you're going to have up here in your environment window, you're going to see where it says seeds. If you click this blue arrow, you can see the attributes. If you click where it says seeds, it'll open up in a new tab and you can see the species, the count, and the weight of the seeds. Great, great. Come back over to the R tab. Get myself out of the way and maybe make myself a little bigger so you can see me. My office is not so beautiful, but this is where I am. It's a quiet space for recording. Yeah, the lecture recording didn't work. So I'm doing this again for you guys. I hope you appreciate it. I hope one person watches it. Jessalyn, you're going to watch it, right? Like Jessalyn, right? Okay, next step. Let's get through this. We don't want to spend all day. I have other things to do too. It's Good Friday. Summary, seeds. Okay, summary. This command, summary, will summarize your data. Oh, yeah, right. Handy. It kind of does all the data, like all the different columns that you have in your data. It's going to make a summary. And this is a really, really good step to do. A really good step to do, because when you're working with your actual data, this will be a step that will help you spot errors. It'll help you spot errors. And one error it'll help you spot is if you see that something read in as the wrong data type, which happens a lot. So in our case, species is supposed to be a categorical nominal variable. Perfect. And that's what we have. Class character. That's the same as categorical nominal. And then count and weight are both numeric continuous variables, which means that we get these summary statistics here. We get the 5-number summary. Remember 5-number summary from the box plot? Min, first quartile, median, third quartile, and max. Wait, that's 5, right? Min, first quartile, median, third quartile, max. Yeah, that's a 5-number summary, but there's 6. Okay, because it also gives us the mean. So we get 6, but that's not part of the 5-number summary, but we do want that. That's good. So count and weight both read in as numeric. And if you wanted to check that, you can also look up here in the global environment tab that when you do this click down here, you can see species, character, good, count, numeric, great, weight, numeric, great. Okay, everything's good. One thing I want you to notice right here is that under species, it says length equals 19. So the length is the number of observations. So we have 19 observations. Somebody collected data on 19 trees. And also that when we look at the count, the median here is about 1,751, whereas the mean is 4,398. That's a big difference. That's a really big difference, right? So remember that, like, if the data are normal, then the median and the mean are going to be the same or pretty close to the same. And if the data are, what's that word? Skewed. If the data are skewed, then the mean and the median are going to be really different. So these are probably skewed data. Okay, so let's look at our weight. What do we have here? We have the median is 216 and the mean is 1,116.51. Oh, also a really big difference. Again, we're probably looking at really skewed data. So this is a good thing to just check. And you can right away see too, okay, the weight minimum was 0.6 and the maximum was 4,535. That's a really big range. Same with count. The minimum was 40 and the maximum was 27,000. Somebody counted 27,000 seeds. Like, were they paid hourly? I don't know. God, geez, that's a lot. What? We're going to assume they did that accurately, and that's a real number. Okay, we're going to make that assumption. We can't go back to the data sheets. We don't have the data sheets. We're assuming this is a good number. And that's probably all right. It's probably all right. You'll see, it'll work out. Now we'll go down to question 3. What is the name and data type of the response variable? And what is the name and data type of the explanatory variable? I ask this question over and over because once you know that response variable, data type, and the explanatory variable, data type, it kind of clues you in right away. Okay, that's my analysis. What's my analysis? That's the kind of analysis I'm going to do. Depends on the response variable, data type, and the explanatory variable, data type, and how many of them you have, right? In this case, we just have one of each. So that already tells us something. So the response variable, which is the response variable? You need to be able to identify the response variable and the explanatory variable when you look at a question. So if you look at this question up here, right at the top, according to the principle of allocation, all this stuff, think about it. Which is the response variable? Which is the response variable? What do we think is, what are we trying to predict? Well, it says the number of seeds will predict the size of seeds. Okay, so we're trying to predict seed size. So this is the response variable. And the number of seeds count is the explanatory variable. And we already looked at our summary, and our data types are both numeric. There's your answer. There's your answer, okay? So now we can type in, I want complete sentences, I demand complete sentences, and Michelle will only give you full points for complete sentences. Let's see, okay. What is the name? Okay, so the response variable is seed weight, which is a numeric continuous variable. Remember, there's 2 types of numeric. It could be continuous or discrete. It's continuous. And the explanatory variable is seed count, which is a numeric continuous variable. Also, good, done. Next. I'm going to put in another header here, assumptions. When you put the hashtag in our notebook, it makes it a big header when you knit it. All right, remember our assumptions for the linear regression? Of course you do. We assume that the data were collected with appropriate randomization and minimal error by our top-notch research team, right? Because we assume randomization, right? We have to assume that it's a random sample and that there's minimal error. So we're not even going to check those. We're going to assume that happened. When you do your own data collection, make sure you randomize. And yeah, of course, you're not going to make errors on purpose. That's for sure. Okay, so here are the assumptions we can check with the data as much as possible, right? First of all, we're going to look at linear relationship between X and Y. It's a simple linear regression, so we need to have a linear relationship. There are other kinds of regressions that don't require linearity, but this one does. All right, and then 2, independent observations. 3, normal distribution of residuals. 4, equal variance of residuals across all values of X. And 5, no outliers with strong leverage. And if you want to remember this as an acronym, it's easy to kind of remember like L, right, for linearity, I for independence, N for normal distribution of residuals, E for equal variance of residuals, and then O for outliers. Lineo, like Oreo, think lineo or line, like for linear regression, line. You want to make a line. If you want to make a line, you got to have linearity, independent observations, normal distribution, equal variance, and no outliers with strong leverage. Out. Great. Now we're going to check the assumption of linearity by making a couple plots, right? So let's make a scatter plot of the data. Plot. We're going to use the plot command. This is base R package, nothing fancy. And we're going to plot the Y variable, tilde, X variable, comma, data, seeds. Pretty simple. And once we run that, we can see this nice little graph that shows us the count of seeds and the weight of seeds. Now, does this look linear? Does this look linear? So our question 4 is, do you think the X and Y variables are linearly related? Like imagine drawing a line, a straight line. Could you draw a straight line? I mean, if you drew a straight line here, most of the points would be so far from it, right? This is not linear. It's curving. It's curving. All right, so we don't have a linear relationship. So we're going to say no. No. The X and Y variables are not linearly related, right? Okay, that's fine. We can handle this. I'll show you how. I keep coming up like look at by picture, but that's not helpful because you're actually like there. You're there. All right. Let's see, what do we got to do next? Let's look at the distributions of the variables using histograms and box plots. That's a really easy way to just kind of see, okay, what's going on with these variables. So if we run this whole chunk at once, what we get are 3 different plots. We get a histogram of seed count. It's bigger for you. We get a histogram of seed count we get a histogram of seed weight, and then we get a box plot showing the count and the weight. Now, if we go back to the histogram of seed count, you can see right away, this is not normal. This is not normal. This is strongly right skewed. There is a strong outlier over here in seed count. Oh, let's scroll back up real quick to that summary seed count, 27,239. That was a lot of seeds. That's what this is over here. It's that one tree that had a lot of seeds. Okay, now we know what's going on. Sure, we can even look at the data. We can look at the data back here. And if you click up on the top, you see there's a really faint gray arrow up and arrow down. If you click that, it'll sort. And now it's sorting from smallest to largest, or largest to smallest if you click again, right? So now you can see that 27,339 count was from the paper birch. It had tiny seeds and lots of them, like a lot, more than something like twice as many as the next tree in the series as the tulip tree. So that's a lot. That's our outlier. Okay, we've identified it. Good. Now we know what it is. Now let's look at seed weight. Here's our histogram of seed weight. You can see this is also strongly right skewed. It's not so extreme of just one value, but we have some really high values and a lot of smaller values. Again, if you look at the data, you can see when you sort it, okay, there's this one very tiny seed, 0.6 milligrams. That's a tiny seed. So tiny. It's like you need a good scale to weigh that seed. And then the yellow birch, 1.6 milligram, et cetera, down to chestnut oak. That's a heavy seed. It's 4,535 milligrams. That's a, it's an oak. It's an acorn. It's a big seed. Now, these are all North American temperate species. If you put tropical species in here, you get, I mean, imagine in Hawaii, right? If you did this for Hawaii, it's too bad you guys have all got your projects. If anyone wants to switch a project, man, do this for Hawaii because you get the ohia, which is going to be like paper birch. It's going to be so many, and tiny, tiny, tiny. And then you got coconuts. How much does a coconut weigh? Several pounds, right? For a good one. That's a way bigger range. That would be interesting to see. I'm sure you could look up the data somewhere. Somebody's done that. I know they have, actually. I've seen it. It's cheating. All right, now let's look at the box plot. The box plot tells us the same thing. It shows us that the data are highly skewed. So the count has this one big outlier, another outlier, and you can see the black line here. Remember, the black line is the median. And normally you want to see the median kind of in the middle of the box. It should be right in the middle of the box. And if it's not in the middle of the box, if it's smashed down onto the bottom, that means the data are skewed, right? Or if it's smashed onto the top, either way, it means the data are skewed. And you can see with weight, the data are strongly skewed, the median smashed down to the bottom. Okay, great. Now we know we don't have a linear relationship and the data are not normal. But remember, we've got these fancy new tools that we can use to fix that. Okay, you can read this yourself, just what I said. So transformations. Now we're going to talk about transformations. What is transformation? Something magical with a wand? Yes, it is. Basically, to transform our data, we run a calculation on each number in our data. Usually we add, subtract, multiply, or take an exponent by the same value for all the numbers in our data. This changes the values, but preserves the relationships among the values. They keep the same relative scales. So let's think a moment about numbers. right? So let's imagine some numbers that can be really big, like 1,000,000 or even 1,000,000,000. Well, these numbers, these really big numbers, can sometimes make it hard to see differences among smaller numbers because they're so huge in comparison. It's like trying to compare the heights of trees when some are towering giants and others are just little sprouts. The super tall ones make the small ones seem tiny. You can barely see them. So people use something called log transformation to fix this, and they use it in all kinds of fields, including biology, to make data easier to work with and understand. Log transformation squishes down big numbers while keeping their relationships intact. For example, let's say we have the numbers 10, 100, and 1,000. After log transforming them, they become 1, 2, and 3, respectively. You can look at the code below, right? I do that calculation for you. Even though the numbers are smaller, their relationships stay the same. So now let's look down here at the code and we'll log transform the numbers so you can see what it looks like. If we just run this one line, put the cursor on this line and hit Control Enter, you see, oops, we got this negative infinite. What's wrong there? If you try to log transform 0, you get an error. It doesn't work. But if you have zeros in your data, add a constant. Just add 1. Log 10, 0 plus 1, that works. It comes out as 0. If you log 10, 10, you get 1. Log 10, 100, 2. Log 10, 1,000, you get 3. You run the whole chunk, you can see how it works. Great. Now let's try log transforming our seeds data to make the relationships linear. So the first thing we're going to do is create new log transformed variables. In this case, we'll use log 10 instead of just log. Log by itself in R gives us the natural log, which is just another way of log transforming. It's fine to use, but I think the log 10 is a little bit more intuitive. This code below is going to log transform the data and save it as new variables in the seeds data frame. So what this does here, log 10 is the function, and it's going to run this function on our count variable inside the seeds data, and it's going to put it into a new variable called log underscore count inside the seeds data. And then it's going to do the same thing where we're going to log 10, our weight variable in the seeds data frame, and store it into a new variable called log weight inside the seeds data frame. And I'm going over this in a lot of detail because some people asked me to explain a little bit more about the mechanisms of R. So you run that and nothing comes out down here, but something does come out up here in the upper right-hand corner. You can now see that we've created 2 new variables, log count and log weight. And if you click over onto our data tab, you can see now we have log count and log weight. Cool, right? And if you sort, you can see that the sorting should be the same, right? Log count is still preserving the relative order of size. And same with weight. So if you click here, you can see that the very smallest one is still the smallest one. The biggest one is still the biggest one. But the range of values is much, much smaller. Now we're going from 1.6 to 4.4 instead of 40 to 27,000. And we're going from negative 0.22 to 3.65, which is a lot smaller of a range than 0.6 to 4,535, right? So we kind of just squished everything down, and that makes it a lot simpler to deal with. Okay, so how does log transformation change the distribution of the variables? Well, we can run the same commands that we did before. So we can look at the histograms and the box plots. Again, we're going to use the hist command, which is in base R, really simple, on our log count this time. And we're going to run the hist command on our log weight. And this box plot command is going to look at everything inside seeds, but it's only going to run the box plots on 4 and 5, columns 4 and 5. So the square brackets select just the 4th and 5th columns of the data. We run this whole chunk, we get 3 graphs. The first one here is our histogram of log seed count. And we can see that our data went from very strongly skewed to something a little bit more normal looking. And by normal, we mean symmetrical bell-shaped, right? Symmetrical bell-shaped. It's not entirely perfectly symmetrical bell-shaped, but it's a lot closer. And then if you look at the histogram of log weight, you can see it's, again, not a perfect bell-shaped curve, but it's not this strongly right skewed curve. You know, it's like, whoa. And if you look at the box plot, well, that looks great. That looks great to me. You know, you've got your median line close to the center, no strong outliers. Yeah, that looks fine. That looks really fine. And they're, you know, the data are in similar ranges, so the variances are not so hugely different either. We've basically normalized our data by log transforming it. This really helps us a lot. And now let's see what happens if we put it on a scatter plot. If we put it on a scatter plot, again, we're going to use the plot command on log weight as our Y variable and log count as our X variable on our data that's in seeds. Run this stuff and we see, hey, now we've got a scatter plot that looks like you could draw a line, you know, you can imagine a line and those points, and you can see, okay, now it looks something like linear. Okay, that looks something like linear. And yeah, now we can do our analysis. Good. So how would you describe the relationship? How would you describe the relationship between log transformed seed count and weight? How would you describe the relationship? Well, we could say the relationship between log transformed seed count and weight is negative linear, right? We have the predicted negative relationship and it is now linear. Great. Let's go on to check our other assumptions. Assumption number 2, independence. Now, this can't really be easily checked with the data, but I do want to show you something that I noticed about our data. And we might ask ourselves, how many species of trees did our team measure? So if you look carefully at the data, you can see that, let's go back over to the data. We have 19 observations. So we might, without looking at the data, just assume that we have 19 different species of trees. And this is a common error I'm pointing out because a lot of people just forget to like look at their data. They're like, they'll run through this whole analysis and never like look at the data. They're just like, okay, got the summaries. Look at the data. Look at the data. Oh, you know, sort by species. Look, there's 2 American beech in here. And there's 2 red oak. Everything else looks like there's just one of them: sugar maple, sugar pine, tulip tree, white fir. Okay. So we actually don't have 19 species of trees. We have 17 species of trees, right? So if you go over to the code, and this code kind of does this for you, is it counts how many unique species. So this unique pulls out unique individuals, the unique values, and length tells you how many. That's kind of like count. If you're used to using Excel, you would use like count, unique. And in this case, you use length, unique. And it puts it into a variable called unique species count. And then I say print the unique species count. You notice I don't always say print. I don't always do that because in R, you don't have to. You can just have the variable and it'll come up. But a lot of other software, they do require you to do that. So sometimes I put that in there just to remind you, okay, this is a way of doing it that you might need later on. If we run that, we can see that the count of unique species is 17. Okay, look at your data, look at your data, look at your data. because it looks like a couple of species were measured more than once. However, looking at the data, it seems like these weren't the same individual trees. So, right, if we look at the data, we can see, okay, the count from this first American beach was 463. And the count from the second one was 1,892. And they had the same weight because I guess that's what you would assume, they have the same weight. The red oak also had two different counts, but at the same weight. I mean, if you really wanted to be strict about it, you could exclude these two or maybe average them. But we're just going to charge forward on this one. I wanted to point that out to you so you could be aware of how non-independence can be sort of sneak into your data. Pay attention. All right, so although it's not ideal, it probably doesn't affect our results too much. Come to think of it, it would actually be way better if all the species were measured several times, and then we'd have like 4 replicates per species, and then you could average them across those or do a different kind of analysis that takes that into account, and that you could get an idea of the effect of species on the seed count and how much it varies within species. But this is what we have for now. So yeah, we're going to roll with it. All right, to check the rest of the assumptions, we first run the model and then plot the results and make diagnostic plots. Remember these diagnostic plots, right? Now we're going to really get into it here. Remember that the LM means linear model and is written with the response variable first, y first, followed by the tilde, then the predictor variable. For example, LM y tilde x comma data my data, right? So this can be read as y is modeled as a function of x. We're going to run the model and store the results of the model as a new object called lm.seeds. Oh, lm_seeds. I changed it, and you know why? I'll just tell you as an aside. I've been learning Python, and in Python, putting a dot means something. It's a dot operator. And so if you put a dot in the name, it could make it go wonky. So I have started changing my dots to underscores so that the variable names would potentially work with Python too. I'm really just at the beginning of my Python journey though. So just starting to do that. Okay, run the next line, and we actually get to now run our analysis. LM seeds, again, LM weight count data seeds. And what we do when we run that is we don't see any results yet, except that we have created a new object up here in our environment. And you can see under data environment in the upper right-hand corner, we have this something called LM seeds, which is a list of 12. Remember, a list isn't just like one thing after another. Like it's not like a list, like a to-do list. It's actually a more complex data structure. It can contain many data frames or vectors. It can contain a lot of stuff. And in this case, it contains something called coefficients, something called residuals, something called effects, rank, fitted values, assign, right? All this stuff. And some of this stuff has other stuff inside that stuff and more stuff inside that stuff. Right? So it's like a hierarchy that can be contained within a list. That's pretty handy as you progress in R. If you choose to go forward in that way, you'll probably end up working with lists. But for now, just know that they exist and that our results are stored inside a list. If you click here, you don't get like the whole thing. You just see, okay, here's the structure of the list, but you can click coefficients and you can see what's in there. You can see, oh, the residuals. Look, those are all the residuals. Those are all the residuals, right? The effects, the rank, the fitted values, call, model, all that stuff. It's all in there. Great, cool. I got it. Now, just for completeness, let's also run the model on the log transformed variable so we can see how it differs from running with a non-transformed variable. So let's run this chunk. So now we've created log underscore or LM underscore log seed. So obviously one of them has the results of our linear model from the log transformed variables, and the other one has the results of the linear model from the untransformed variables. And before we even look at the results, we're going to check the assumptions here. We're going to check the assumptions. We're going to start, I'm trying to go in order here. So number 1 was linearity. Number 2 was independence, right? Linearity, independence. Now we're going to go to N, normal distribution of residuals. So to check that, we plot the model results, and I'm going to just look at the QQ plot, which is actually kind of a measure of normality, actually. So, but I'm going to use the plot command, but instead of plotting an XY, what I'm plotting is the results of the model. I'm plotting the results of the model. This is how you do the diagnostics. This is how you check your assumptions. You run the model and then plot the results of the model. And in this case, which is going to give me just the second plot. I'm also going to make a histogram of the residuals. So I'm going to use this hist command, what we used before, to look at the distribution of the variables themselves. But now I'm not going to do a histogram on the variable. I'm going to do a histogram on the residuals of the regression. Remember the residuals? Residuals are, okay, you've got your line, in this case, line going down, and you've got all the actual dots of the data, and then you've got the line. So how far what's the distance between each dot and that line? That's your residual, right? Each dot and that line, that's your residual. And so that's kind of your error, like how far off is the line? And you want the errors to be about the same all along the line. That's the, equal variances and normally distributed. You want like some little ones, some bigger ones, and then a bunch in the middle, right? That would mean there's nothing wonky going on. And one way to do that is just by making a histogram. And again, we're going to do that by taking this item out of the results, which we look at, right? Remember here, LM Seeds, if we look at this tab, LM Seeds has this thing, residuals, has this object called residuals, and you can access it by typing the $sign and then saying, take this residuals thing out of this object. Okay, cool. And make a histogram of it. Now let's do that. And I personally really like this because I like looking at histograms. Histograms make sense to me. The QQ plot really actually tells you, like if, oh yeah, that's right. We're doing the QQ plot on the residuals. Okay, good. Yeah, that's right. So we're looking at the normality of the residuals here. So remember with the QQ plot, you would have like the dots all along the line. They're not. They're like a long tail over here. And if you look at the histogram of the residuals, you can see that the residuals are also right skewed. So the data were right skewed and the residuals are also right skewed. So we know something's going wrong with our data because we have like a lot of really small residuals and then a few really big ones. Not what we want, right? So let's try the same thing with the log transformed regression. So if we plot the results of the linear model of the log transform data, and we look at the QQ plot and also the histogram of the residuals, then what we get here is the QQ plot on the residuals. It does still kind of show them going off the line. And I know these are kind of like hard to interpret, but at least it's not going off the line strongly on one end versus the other. It's a little bit better. And then the histogram of the residuals, you can see, okay, well, that's a lot better. I mean, it's not a bell-shaped curve, but they're even, right? So you don't have like a strong skew off to the side. So better. Okay. Next, if you look at assumption 4 is equal variance of residuals across all values of X. How do we check that? Well, we plot the model results and residuals versus fitted and look at the standardized residuals versus fitted. So we look at these two plots that come out of plotting the regression results. And it's the first plot and the third plot. You don't always have to remember that. You can just hit plot the results and look at them, but you do need to remember what it is that you're looking at. And this is the one that I think is the most simple to interpret, is the residuals versus fitted, because the fitted value is basically the value of what the predicted line, right? And the residual is how far off it is from the predicted line. And you can see that remember I said you don't want your data making faces at you. Well, this data is like smirking at you. It's like, you have a very high residual at this very low fitted value, right? You've got a very high residual. And then you have some intermediate residuals. And then again, you have very high residuals, right? It goes up. So these are the high residuals. And that means that at either end, you get really high residuals. And that's not what we want. We want it to be relatively even. So we want that red line to be kind of flat and horizontal. And if you look at the scale location plot, you can also see there's a strong kind of a V shape going on here. That's not the flat line that we want. Looking at the scale location, which is basically the fitted values versus the standardized residuals, which is just another way of looking at the residuals. Okay. So again, looking at the residuals versus fitted plot, you notice that the residuals sharply increase at the high end of the fitted values, and that's a sign that the difference between the actual values and the predicted values or residuals are not constant, because they increase as X increases. We want them to be about the same throughout the range of our X values. So let's do the same for our log transformed variable model. Let's plot these residuals versus fitteds. And we can, again, get these two plots. And you can see that residual versus fitted, now it's kind of a frowny face, but if you look at the points kind of look just like randomly scattered. There's no pattern to them at all. And I know this still looks like, I really should replot this. Like, and I'm just going to ask you to imagine this, but look at the scale here. This scale goes from like negative 1 to positive 1, roughly, right? It's like negative 0.5 to 0.5, right? That's our scale, and 0 is in the middle, right? The 0 is always in the middle. So it goes from like about negative 1 to positive 1. And if you were to plot this same fitted versus residuals onto this plot up here, which goes from negative 1,000 to 3,000, then like that negative 1 to positive 1 would be like right here. It would look like it's right on the line. It would look like it's right on the line. It's just, remember when we talked about graphs, I think it was day 1 of class, and how if you have different scales of the axes, it can kind of make it look like something's going on that's not going on. So yeah, if you put all of these on the same scale, you would see it looks like a flat line in comparison. I mean, this is a really huge variation of the residuals. So, no bueno. But this is good. This is fine. This is okay. We fixed it. And if you look at the residuals versus fitted with the standardized residuals, this is the scale location plot. It's still fitted values, but standardized residuals. Again, you can see that this is very nice. So the points look just scattered, and the red line is roughly horizontal and flat. So we're okay. Yeah, it's good. Yeah. Next, let's check outliers. Number 5, linear outliers. Now remember, outliers are only really a problem if they also have strong leverage. So if they are pretty far off on one end or the other, and they're actually pulling the line, so changing the line like a lever, right? Think of leverage. They're pulling the line like a lever. That's not good. And how do we measure that? Actually, this one is the easiest one for me to interpret, because there's this handy thing called Cook's distance. And Cook's distance is like, it's this nice, well-defined little line that we'll see on the graph. And so if your Cook's distance is less than 0.5, it's fine. If it's more than 1, it's a problem. So let's look at the model results. In this case, we're going to plot the linear model results from the non-transform model, and we're going to say which equals 5 to just see the leverage plot. And when we look at that, we can see that in the residuals versus leverage plot, there's one point that falls way outside of the dashed gray line, this one over here, indicating that this point, right, point 1, has really high leverage, meaning that it has strong influence on the slope of the regression line. And what is this point? What's point number 1? If we go back to our data, what is point number 1? Is it, what do you think? Is it this paper birch? Right? Right? The big outlier also has strong leverage. Interesting. So we go back to our code and we can say, okay, that's that one. Other ones also are problematic. They're showing up with their numbers on them, but this is the one that's really giving us a problem because you can see this dashed gray line shows us our Cook's distance. And if it's outside of these dashed gray lines, especially outside the 1, then okay, you've got a real issue. But if we log transform the variables and we look at that plot, we can see, oh, yay, everything's all right. Good. So our Cook's distance is, everything is within the Cook's distance of less than 0.5. So we're good. We fixed it by log transforming. No bueno, okie dokie. Right? So how does log transformation change our diagnostics? Well, it changes them in a lot of ways. And I want you to really write out a description of this. Okay, so the first thing that we saw, oh, this is a lot, right? This is a lot. Okay, what was our first one? Okay, linearity, L-I-N-E. Okay, I'm just going to put it out here, L-I-N-E. Oh, right. It's going to help us with all of them. How does log transformation change our diagnostics? Well, for linearity, okay, we can see that log transformation made the scatter plot linear, right? Showing that we now have a linear relationship between the variables, right? So this meets our assumption 1. And then independence, well, log transformation did nothing for that. Let's just get rid of that one. But normality of residuals, right? So log transformation made the highly skewed residuals roughly normal, as we can see from the, which ones did we do that? Oh, the histogram of the residuals. Right, good. Right, so I'm going to say what we found and where we found it. So we looked at the scatter plot. Okay, it was linear. So we now have a linear relationship between the variables. Log transformation made the highly skewed residuals roughly normal. And how did we find that out? We looked at the histogram of the residuals, right? And then equality of variances. So we looked at, say based on the residuals versus fitted values plots, we can see that log transformation made the residuals more equal across the range of values, x values, right? So we made them evened out. Good. And then outliers. Okay, we had a big outlier. So we found there was one strong outlier, or one outlier, let's say one outlier with strong leverage. And we can even specify that, like Cook's distance greater than 1. I don't know exactly what, we could pull that out, but it was greater than 1, so no good. But the log transformed data had no points with strong leverage. I mean, you could make this like a prettier sentence. I'm just like putting it out there so you can, oh, this is how we test that assumption, right? With strong leverage. And then you say, okay, like the Cook's distances were all less than 0.5. Great, cool. So that's how you can answer that question. And I do want a thorough answer. And when I ask you for this on the test, which I may ask you this on the test. I want a good answer. I want you to describe what you see. You could even be like, look, we could see that it was smiling at me. I didn't want it smiling at me. I didn't want it frowning at me. I wanted to be like, right? I wanted to be like that uncle that just sits on the beach, like, yeah. All right. Results. Yay. Now we can get to the results. Now we can take a look at the results. I'm so happy that we actually get to look at the results. Okay, just for fun, again, we know that the linear model with non-transformed variables is not valid, but we're just going to look at the results so you can see what that looks like. So we run this here and it's going to say summary. Oh, summary. Remember the summary command before? And it did something entirely different. When we ran the summary command on our actual data, it gave us a summary of the data, but we run the summary command on our linear model results and we actually get our results. Hey, just for funsies, what would happen if you just selected LM_seeds and you ran that? Oh, is that what you want? No, that's not what you want. You get your coefficients and the count and stuff, but that's like, no, I mean, yeah. Well, you want the whole thing. So you run a summary of it. That's how you pull out the results in this nice table that we're familiar with by now. It starts off with telling us the model that we ran, right? The call, the formula, weight as a function of count on the seeds data. And then the residuals. And I know some people, I think, don't get this depending on the version of R that you're running, but I like it. It's handy. It shows you the 5-number summary of the residuals. And remember that the 5-number summary gives you an idea about the skewedness of the data. So if you're get a 5-number summary of your residuals and you can see like, okay, my minimum, now I don't have the mean on here, but the minimum is negative 1,345 and the maximum is like 2,969. So that's like a really big difference. That does not look like it's going to be symmetrical around the median. And we kind of want that median to be like 0. That would be perfect, right? It's not. But we knew that already. We knew this was going to have problems. That were right. And then we look at our coefficients, right? So the estimate here of the intercept, right? This is our estimated intercept. Again, the intercept is just literally where the line intercepts the y-axis. What we have here, this is seed count, right? That's our x variable of interest. And this is our estimate. So this is our slope. This is our slope. Remember, y equals ax plus b. So this is our a. This is what you multiply by x plus intercept to get your predicted value for any value of x. Right? And you got the standard area of the t-value. But what I really want to show you here, okay, what I want to show you is this. Look. Okay, our p-value. We always want to look at the p-value. Everybody's like runs to the p-value. Our p-value is like less than 0.05. We have A star. Cool. We have a significant relationship. Boom, boom. Null hypothesis rejected. Oh, print out the paper. Send it away. No, wrong. No, because it's not just about the p-value. It's about other things. Even though we have a significant p-value, this estimate is tiny. Like this is not even 1. That slope is significantly different from 0, but not by much, not by much. And then also look down here. Okay, so our multiple r squared, like our r squared value is 0.2206. So what is that telling us? Remember that the r squared value tells us the proportion of the variation in y that can be explained by x. So basically 22% of the variation in seed weight can be explained by seed count. Okay, so 22%, like that, you could throw a party for some kinds of data and you could say, hey, that's great. we just explained 22% of our data with one variable. Maybe that's awesome. But I'm going to tell you, it's not. And here's why. Check out the next one. The next one, if we look at the summary of the log transform data, boom, right? Okay, we got a similar thing. We looked at the log count. Yeah. Okay, our residuals, check it out now. I was walking through this little by little. Now look at our negative on the residual. It's like negative 0.7, right? That's the minimum. And then the maximum is 0.69. You see how that's kind of symmetrical? And then the median is really close to 0. Okay, so now we're getting some symmetry. We're probably getting more normality in our residuals. And then if we look at our coefficients, right, the intercept is now 6. Okay, this is actually like not as easy to interpret because we log transformed the scale. So it's not so meaningful, but you can see that the slope is now negative 1.5. So we're thinking of absolute value. This is a lot different than 0, a lot more different from 0 than what we had here was like negative 0.1. Now it's 1. And again, this is hard to interpret because this is a log transformed value. So it's not that the slope is 1.5. That's how you would do you have to back transform it. But you can see that you've just increased your effect size. You've increased the, effect, kind of. We can predict better. And how else do we know that? We also know that by looking at the p-value. Now, look at that p-value. It's really tiny. I mean, it's itty bitty, right? And again, it's not just all about p-values. It doesn't really matter, maybe. I mean, there's different schools of thought. Some people are like, if it meets the cutoff and it's significant, it's significant. If it's, p-value doesn't matter after that. And some people are like, well, highly significant is like a really tiny p-value. And different people have different thoughts about that, but I'm thinking this makes a difference. And then if we look down here, this is where really we get something important. And so we look at our R-squared value. That's a big difference, right? And we went from 0.22, we got before we described 22% of the data. Now we're describing 86%, 0.8631. We just like quadrupled almost our predictive power. That's a lot because we met the assumptions, we checked. Now, if you had not checked your assumptions, if you had not made a scatter plot, if you had just run the analysis and you had gotten these results, you might just write your report and say, okay, look, it's a significant effect. And this is how much it predicted. Boom. No, but if you spend the time to go step by step through the diagnostic plots and check it all out and do a transformation that actually works, and some work differently than others, and you have to play around with it sometimes, but you're likely to be able to significantly increase your predictive value. And when I say significant, I am not testing a p-value there. I'm just saying it's going to be a lot. Great. Awesome. Now, okay, so how does log transformation change our results? Refer to the p-value and R-squared. So what did I say? Okay, log transformation, when I don't know how to answer a question, I just start by repeating the question. Log transformation improves, that's how it changes it, right? Improves our results by increasing our effect size, which is our slope, right? And you can even write in like your slope value before and after. I'm just saying like our slope, right? And then decreasing our p-value and increasing our R-squared. And I'm going to say from 0.22 to 0.86. Right, that's a big difference. That's a big difference. So basically what that increased R-squared tells us, the increased R-squared tells us that the regression model now fits the data much better. Because that's what the R-squared tells you. It tells you how well it fits. How well it fits better, way better. Okay, so now let's plot it. Let's look at it, see what it looks like. Okay, cool, look at that. There is our data with the line, and you can see these points are falling along that line. They're falling on that line. And the distance between the points and the line are not like huge on one side or the other. It's all about roughly the same. Some are right on the line, some are a little bit further, some are kind of halfway in between. That's our normally distributed residuals. Perfect, right? Okay, so do we now meet the assumption of linearity? In other words, does the regression describe the data pretty well? Yes, right? Yes, we now meet the, I keep telling myself, slow down to go faster. If I get too hurried, I know, because I like want to get through this. It's going on too long. I'm sorry, this lab is too long. You can listen to me at like double time. That's fine. I would not be offended. Is it like this? You could, all right, the data now meet the assumptions. We now meet the assumptions of linearity and the regression line now describes the data much better. Okay. So predictions with the log transform model. Okay, now we're going to get into something else. And this is something else a little bit new. We've talked about it a little before. Yeah, we did this before. We did this prediction thing. I think I put this on a quiz. Yeah. Okay, so it's just a little trickier with the log transformation. So remember that we log transform the variable. So we change the regression equation, and here we're writing it as y equals beta 0 plus beta 1 x1, which is, so like, remember, beta 0 is the intercept and beta 1 is the slope, and then of course x1. Of course, we only have one here. So remember, with the multiple linear regression is when we first started looking at this, and we had like beta 1, x1, beta 2, x2, right? And so now we're changing it to essentially this. It's log y is equal to the intercept, beta 0, plus beta 1, or the slope, times log x1, right? So to predict the change in seed weight for every unit change in seed count, we have to back transform our coefficients, right? So we need to exponentiate. We need to exponentiate our coefficients. So there are a couple different ways of doing this. So you think about like transforming and back transforming. So if we use log 10 on 100, you get 2. So now if you take 10 to the power of 2, right, power of this 2, you get 100. That's how you go back and forth, right? So if you take log transform 1000, you get 3. And 10 to the power of 3 is 1000, right? Go back and forth. Great. So if we had used the natural log, just as an aside, which is the log command, we would use exponentiate to exponentiate our coefficient. So log 100 is 4.6. And if we exponentiate 4.6, we get close to 100 with rounding error. Does that make sense? Okay, good. So now we want to predict the change in seed weight. Predict the change in seed weight from seed count using our log model. I hit something. I changed my cursor. I do this all the time. And now, okay, good. Predict the change in seed weight from seed count using log model. Remember that the slope from our output is a change in log seed weight for every 1 unit change in log seed count. All right, so let's pull out the coefficients from the model. And how do we do that? Well, we have our linear model log seeds, which stores the coefficients, stores all the results. And to access the coefficients, we've used the $ coefficients, and that's how we pull the coefficients out of it. And if we run this, just this one line, you can see that we just pulled out our intercept and our log count, right? Those are our values from here. Intercept 6.7, log count 1.5, right? We're just kind of pulling it out, so isolating it. So we can then do some other math on it, right? This, I'm just showing you. That's how we do it. Now I'm going to say, I want to take the coefficient of from this log seeds, and I'm going to take number 1. So if I'm just going to show you, like if I run coefficient log seeds, I get, again, those same two things. But now I'm going to use the square brackets to say, just give me the first item from that thing and store it into something called beta 0. And now my beta 0 is that intercept, right? And now I'm going to do the same thing. I'm going to say, give me the coefficient from the linear model on log seeds and give me the second element. If I just run that, I get log count. And now I'm going to say, store it inside of something called beta 1, because now it's like the same name as the equation, and I can just plug them into the equation, right? And now if I want to look at those, I can say print beta 1, beta 0, print beta 1, right? You see all of them. And if I want to back transform the slope, which actually isn't necessarily what I want to do, but yeah, and I get log count. I don't actually need to do that. I don't need to back transform the slope, but anyway, I put that in there. So to predict the weight of seeds for a tree that produces 1,159 seeds, which is the value for sugar pine, which is roughly close to the mean. Sorry. Okay. So we just plug it all into the equation. Here's our equation, right? Log 10y is equal to beta 0 plus beta 1 times log 10 x1. So what's our x1 is this 1,159. And so we're just going to plug that in there, right? So we've already defined beta 0 as our intercept and beta 1 as our slope. We saved those up in the previous step. And now we're just going to run this log 10 transformation on this value for sugar pine, 1,159. And we're going to store that over into something called log 10y. Run that. And then what we get here with log 10y is 2.06, which is the log of the y, the log of the weight for seeds for a tree that produces as many seeds as a sugar pine, to see if our prediction is close, right? And now we have to back transform it to get back to our units of milligrams. Otherwise, the log transformed value doesn't have units anymore. So to do that, we're just going to say 10 to the power of that log y, and we get 115. So it would be 115 milligrams is the predicted weight of a tree that produces 1,159 seeds. Okay, so let's look at our sugar pine. Okay, the sugar pine seed weight was actually 216, so not super close, but you know, it's in the ballpark. It's not 2, right? It's in the range. All right, so question 9, this is for you to do. How much do we predict a seed will weigh from a red oak tree that produces 253 seeds, right? So, or a tree that produces, how much will the seeds weigh from a tree that produces 253 seeds, which is the value of red oak. So we're going to see how well we can predict red oak from our analysis, which is like close to the median. And, you know, if I'm this, I would just copy and paste the same thing and then just change the number. So like if I were you, I would just go up to this previous chunk and I would just take all this code and then copy it and then put it into this empty chunk. And now we want to predict the value for 216. So I would take that number and I would replace 1,159 with 216. Oops. Right. And now this is going to run the regression equation for 216. And now we'll get the log y for that. And then we can back transform it and we get 1,493.596. That's how you do it. That's how you can run the math. You can use R as a calculator to do it for you. And an easier way to predict, and this is how you would do it if you want to do it for more than one value, is to use the predict function. And to use the predict function, what you first do is create a new data frame with the count values that you want to predict, right? So you could say, in this case, we're just going to predict one value again. We're going to say we're going to make a data frame. So we're going to use the data frame command, and that makes it into a data frame, even though it only has one value. And we're going to create inside that data frame an element called log count, or a vector called log count, which in this case is equal to log 10 of 1,159. And we're going to store it in something called new data. You could call it whatever you want, but this works. And then what we're going to use is the predict function on using the results of the regression LM log seeds and putting in the new data. New data equals new underscore data. This is what we created. And we'll store it into an object called weight predicted 1,159. So if we run this, and then we back transform our weight predicted 1,159, so 10 to the power of that, we get 115. So we get the same answer. It's just another way of doing it. Just another way of doing it. Instead of plugging in the number to this equation, we plugged it in to first a new data frame and then use the predict function. And so this actually looks harder and clunkier, but if you had a lot of values, this would be a lot faster. So you can use this to check your math, write the code to use the predict function to predict the weight of a seed from a tree that produces 253 seeds. Now, again, if I were you, I would just copy this code from the chunk above, just copy that, and then paste it down into the empty chunk. And then all you have to do is change this number 1,159 to the number 253. And then I run this and I created a new data. Remember, new data is now just the log transformed 253. And then I use the predict function on that new data. And I'm going to change this number here. Instead of 1,159, I'm going to make this 253. And again, change this. Remember, you got to change it in both places. You got to change it all in, or 1, 2, 3 places. And we're going to back transform that value. And now we get 1,174, which is the same thing. Oh, no, we get a different number. Oh, I put the wrong number in up here. That's why, sorry. It should not be 216 here. It should be 253. Oh yeah, and now it is 1,174. Okay, so both methods give you the same results, just a different method. All right, so conclusions. Now we can present our results to the world and write our conclusions with confidence. So we're going to start by making a nice little graph. And this is a really simple graph. We're just still using the base R plot function. And our Y is log weight, our X is log count. The data are the seeds data. But what we add here that's a little bit nicer is using the main command, we add a title. We're going to call it Seeds of North American Tree Species. And using the XLab command, we add a label to the x-axis called number of seeds. And using the YLab command, we add a label to the y-axis called seed weight in milligrams. It's important to put the units if you want full points. Full points require units and labels. And then we're going to add the line, ab line, from the results of our linear model. And that adds the least squares model from the regression. You have to run this whole chunk at once for it to work. If you run them as separate commands, it gets confused, right? It gets confused. So just run the whole chunk and then it works. And then you have that same scatter plot, but now you have a title and you have labels for the axes, which is really important. Let's wrap this up. So to write our conclusions, do our data support the principle of allocation? Yes, they do. So we can say our data support the principle of allocation. Colon, you can use a colon here. Trees that produced, past tense, few seeds also produced heavier seeds, and trees that produced many seeds produced lighter seeds, with some variation, right? Okay, and we can say the slope of the relationship between log transformed seed count and log transformed seed weight or you can say between log seed count. It's a little tidier, between log seed count and log. I see it in papers like this. Oops. Oops, why is it doing that? And log seed weight. Was negative. Okay, cool, because this is where you can put in your results. What was our slope again? Up to the results. Where was the results? Oh, there it was. There are our coefficients. Our coefficients are right here. There's our slope. Okay, our slope was negative. Let's just take negative 1.52. Boop-a-doo. Drag that down to our, okay, that inside the parentheses. And our P was equal to, oops, let's say P was less than 0.0001, right? That's one way to do it. And key point, put in seed count or log seed count predicted, was it 86%? That's the R squared, right? Of the variation in log seed weight. I think we could even say it like this. Seed count was a very strong predictor of seed weight, with log seed count predicting 86% of the variation in log seed weight. Great, cool. So now we have conclusions that refer back to our original idea of the principle of allocation. And we explained, yes, okay, we found that trees that produce few seeds also produced heavier seeds, and trees that produce many seeds produced lighter seeds. And we refer back to our results here. The slope of the relationship between log seed count and log seed weight was negative. And here is our slope, negative 0.52. And we put the p-value for that slope, right? Highly significant. Oh, what was the t-value? T-value for that slope. Get back up to the results. Okay, the t-value is negative 10.35. Okay, so let's grab that. Put that in there. Oh, okay, here we go. Okay, so we already said that that was the slope, and then we can say t is equal to negative 10.35, P less than 0.0001. And then seed count. Remember, I always want you to do this. I always want you to have the results stated in there specifically. Seed count was a very strong predictor of seed weight, with log seed count predicting 86% of the variation in log seed weight. And I know sometimes you would be okay to say just seed count predicting 86% of the variation in log seed weight. And then in the methods, you would say, hey, we log transform these at a time. And then you could even say something like, oh, in general, our prediction was fairly accurate. And, you could talk more about your predictions. But this is good. Okay, bonus section, you guys, quadratic terms. So there are lots of different ways of trying to fit a model that is nonlinear. And one way to fit a nonlinear model is to add a quadratic term to the model, which is x to the power of 2. And here's how you do it. You can create this quadratic model, which is a linear model with, in this case, weight as a function of count, plus this quadratic term, I count to the power of 2 on your seeds data. And if you run that, you can see that you have the count variable and the quadratic term are both significant. So they're both fitting the line more or less, but your R squared is 0.43. So it's higher than for the linear model, but nowhere near as high as for the log model. And if you plotted that just to get an idea of what it looks like, you could first generate a sequence of count values for the plotting. And then you could use this predict function again to predict the weight values using the quadratic model, and then plot those data points and add that line from those predicted data points to the regression model and see how well they fit the actual data. And if you do that, you can see this red line that's your predictions from the quadratic model, and it's curved, right? And it kind of goes below the y. Wait, I should probably set my y lim equal to, kind of embarrassed. I feel like people are going to look at me and be like, oh my God, she doesn't know how to set the plot function. No, I don't. I never do. I look it up. I figure it out eventually. If I really have to, I will. But right now, it's not that important for what we're doing. So I'm just going to move on. Okay, next, scale the data. Here is another way of transforming the data that is very powerful, called scaling the data. So in the context of standardization is a pre-processing step that transform the features or variables in your data set to have a mean of 0 and a standard deviation of 1. It makes everything shrink down to mean of 0, standard deviation of 1. This is also known as z-score normalization. This helps in comparing the relative importance of different features because they are now on the same scale. Everything has the same mean and standard deviation. By scaling the data, you remove the units of measurement and each feature becomes dimensionless. This process is particularly useful when the features in your dataset have different scales or units of measurement. It ensures that no single feature dominates the others in terms of scales or variance, which can be important in certain algorithms like gradient descent-based optimization or when using distance-based methods such as k-nearest neighbors. Additionally, scaling can help with the interpretation of coefficients in regression models. Since all variables are on the same scale, their coefficients become directly comparable in terms of their impact on the outcome variable. So to do it is really, really easy. You just use this scale function. That's it. That's all you have to do. So you just run scale on your variables, and now you've created new variables. If we look up here in our data, we've now created weight scaled and count scaled. And to analyze the data using the scaled variables, you use the same model, linear model, but now you do it with the weight scaled and count scaled on your seeds data. And you can plot and summarize the model as such. And now you can see that if you plot the scaled data Residuals versus fitted still looks absolutely awful. Well, actually, it's not as bad. I mean, it's still it's definitely got a nasty smirk, but at least the range of the residuals isn't as far off. The QQ residual plot, no, it doesn't really look better. The scale location plot's still no good. Ooh, still really strong leverage on that one. Okay, and our results show us that our estimate is tiny. P-value is the same significance as our untransformed variables, and our R-squared is the same as our untransformed variables. So this didn't really actually help us at all. It didn't help the model fit better. Sometimes you have to try different transformations and just see what works. And hopefully you were able to complete this entire lab in the amount of time that I've been talking, which is already like way too long. Sorry. But I've been very thorough. I'm very thorough. And you should have all the information that you need. Eddie is over here napping. Okay, let me show you how to knit the assignment so you can submit it. Now that you've done everything, save it, right? Save it. And then go up here to knit. You see the little ball of yarn and the knitting needles? Go to knit, knit options, knit to HTML is the easiest one. And it'll just start running through all the chunks. You can see 45, 85, 9, and 100%. And what you get here is this nice HTML file that gives you a nice title, and all of your questions will have this nice grade line next to them. So that makes it easy for Michelle to grade.